Balancing of two terminal elements. So the only way we can add things, we need to add, we need to reproduce the error and we need to subtract or add. So how do we add two things? Well, we can add voltages by placing two elements in series, and we can add currents by placing two elements in parallel. This is how we can add in network theory. That's basically all we have with two terminal elements. So here you see we have two elements, and one we place upside down. Two nonlinear elements, let's say nonlinear resistive elements, so they are resistors but non-linear, and the linearity is indicated by the extra line in the resistor, and you see that one is flipped with respect to the other. So that is called an anti-series connection of equal elements. And now you see that we add the two voltages, but if you consider the nonlinearity, then both the current and the result are flipped in one element with respect to the other. So this is how we have implemented this balancing technique. Another technique is using a complementary element, which is, of course, for two terminals elements, the same as flipping the original element around. And if we look at the curve, um, so without doing the mathematics, but just see how it works, then you could plot from both elements the voltage to current relation, and we are going to add the voltages for the same current. That is basically what we do. So we need of both elements in this situation the voltage to current relation. So let's do it for the red one. We just plot something here. So let's say the red one has this voltage to current relation, and the other one, the green one, is either flipped around or complementary, which means that this curve is rotated over 180 degrees because both the argument and the results have been swapped of sign. So that's what you see if you rotate this curve over uh, over 180 degrees. And what we do now is we are going to add both voltages because we have placed the elements in series. And if we do that, then you see in the origin, so for I equals 0, that we have an equal positive part at 1 to the negative part from the green one. So the red one and the negative exactly cancel. But for high currents, high positive currents, the green one will dominate, will win at the end. And for large values of negative current, the red one will dominate at the end. So the highest voltage takes over, in fact. And the result looks like this. So here we simply add the voltages of the two things together, and we get the blue line. So this is then compensated, and you clearly see now that we have created an odd function because you can rotate this function over 180 degrees and it remains the same. So it has only odd terms. If it would only have even terms, then you could mirror it around the y-axis. But this is a function having only odd terms. So we can also do it with complementary elements. Sorry, sorry, I first want to go to biasing. So we have discussed biasing, and biasing, you remember with a two-port with a transistor required um, four sources. And if we do it with a nonlinear resistor, like a diode, for example, it requires two sources. You can see if we drive one current, if we drive IQ through a non-resistive element, a passive element, then it will generate a voltage, and VQ exactly compensates for that voltage. So the series connection, the series voltage plus minus Vs is exactly zero when we are in the quiescent operating point when we apply no signal. And there is no current as well. So you can terminate this two terminal element with any other elements. You can place it in series, in parallel, and there will be no current through it or voltage. I want to add another voltage, which I call the common mode voltage, which is VC in the picture. It is like, consider that we have a V plus at one terminal and V minus at one terminal and some kind of V common mode, which is of course VQ minus VQ and the plus VQ, sorry, at the VC node. And now, if you look between the plus and the minus terminal, you wouldn't see any result of VQ because one compensates exactly for the other. And you would also not notice this current IQ. So there will be current flowing through the devices, but you will not note it externally. And also the bias voltages you will not see externally, as we have seen, of course, also with amplifier stages. We could bias this configuration also in this way. We could split the current source over ground, redirect it over ground. So then it goes from the common mode VC node to ground, and from ground to the V plus node, or from ground to the V minus node. And that's what I have done in this picture on the right. And then you see basically that the bias voltage can be observed as the common mode voltage. That was already there, of course, on the common mode voltage at this node, because now we have eliminated VQ. So we changed the voltage VC after elimination of this VQ. So you could say elements can be biased with common mode sources if we have anti-series or complementary series connection. Bias voltage appears as common mode voltage in the circuit, and that is an important conclusion that we can later on use also for two terminal, for two port elements. So this is about the biasing and about the large signal characteristic. Let's go to the small signal behavior, the small signal model. It's quite obvious, of course, that you now just have to have the derivatives of the VI curves in series. So if we talk about resistors, it would only be R1 and R2. But if there is also charge storage or flux, then we better say, use the symbol for impedance here. So the total impedance equals the sum of the two impedances. So if the device is working in the quiescent operating point and we have equal devices, then of course we can simply say that the total impedance is 2 times impedance of one or the other. So that is only in the quiescent operating point, because maybe it's good to go back to this point. If we apply an external current through this device, then through one device the current would increase, while through the other device the current would decrease. So both are coming in another operating point, having other derivatives, having other uh, small signal resistances. The noise. The spectral density, the noise spectral density of the voltage is a sum of the two spectral noise voltage spectral densities, as simple as this. And again, if both are equal, then it would be just 8 kT times the real part of Z, and which is then Z1 or Z2. So this is a noise model for the two. Let's go to the parallel connection. The anti-parallel and the complementary parallel connection. How does it work? Well, basically the same. We have to change voltage and current, and then you have exactly the same story. So we have here the current added, the current through one element plus the current through another element is the total current I. So there will be only odd terms of this parallel device. So here we have two complementary elements in parallel, and the first is two anti-parallel connection of equal elements. It's just a matter of naming, and it's important that you now already see that we can use anti and complementary as terms that can replace each other. So we can do the same, of course, but now we have to write the current as a function of the voltage, and then we can add the two currents, because now the two elements are in parallel and not in series. So if you do the same curve, but now we call it an IV curve instead of a VI curve, then we have for the red one, this curve, for the green one, rotated over 180 degrees, and the sum, of course, is passing again through the origin, because all even terms cancel. So this is exactly the same, of course, as with the voltage. You just swap the axis and the arguments and results. The biasing is like this. We have biased each element again with the two bias sources, as we did exactly the same in the other situation when we placed them in series. But now we place them in parallel, and you see quite easily that IQ through one eats the other one. So IQ cancels. IQ is not observed at all, but there will be a current flowing in the devices, which is of course set by VQ. And the VI characteristic of the device. So this current, now I connected one point to ground, and we just apply a parallel current, just a total. And then you see that the common mode current is this IQ. I shifted the VQ, I placed the ground between the two. So, and draw it a little bit different, but this is exactly the same picture as the other picture. But now with one midpoint grounded. And here you see the common mode current flows and is set by the bias voltages and the nonlinear VI characteristic of this element. And it cannot be observed at another place as a current through the power supply or a current through the thing, but externally you don't see it, of course, because that is what we call the differential mode quantity. This IP is a is differential mode, and ICM is a common mode current. So elements can be biased with common mode voltage sources, that is exactly dual to the other situation, and bias currents appear as common mode current in the circuit. Also, we can make a small signal model, and I think you can already guess what is going to happen. It will just be the parallel connection of the two admittances, and this you find them as a derivative, of course, of the VI curve in the sorry, in the of the original devices, the operating point. So if both devices are in the same operating point, I1, Y1 will be the same as Y2. So the small signal admittance is the sum of the small signal admittances of the constituent element, just as the small signal impedance was the sum of the small signal impedances of the constituting elements with series connection. This is just simple network theory. And if they are both equal, then you might as well write this. The noise is of course also the same, but the dual situation. Now we have to deal with the current noise spectral density, which is the sum of the two current noise spectral densities of the constituting elements. So it's like this. We have two elements in parallel. Each has their associated noise current with their associated spectrum, and the spectra, the total spectrum is the sum of the individual spectra. And of course, if y1 and y2 are equal, then we have just HKT y, and y is then I1 or y2. So this is about two terminal elements, and we are going in the next presentation one step further. We are going to two ports.